In this video, we consider whether the following statement is true or false. Context-free languages are closed under intersection. To start off, let's consider two languages. Let's take languages L1, which is going to be the strings of the form A to the M, B to the N, C to the N, such that M and N are greater than or equal to 0. And the language L2, which will be strings of the form A to the N, B to the N, C to the M, such that M and N are greater than or equal to 0. So first we need to prove that these are both context-free languages. So let's start with L1. How do we prove that L1 is a context-free language? We could give a context-free grammar. So let's call it G, and G is going to be a set of variables. It's going to have a set of terminals. It will have a set of rules, and it will have a start symbol S. Okay, so let's create grammar G. So we're going to let the variables, well, we'll define the variables after we define the rules. That'll be a little easier. So let's define the set of rules or productions. So for L1, we want strings that look like, let's do like A, B, B, C, C. That'll be in the language. Or A, B, C. That'll be in the language. Strings like this. Okay, so the important thing to note is that A can be generated independently, but B and C need to be generated in pairs so that we have the number of B's equal to the number of C's. Okay, so let's start off with our start variable S. And let's produce the A's separately, and let's make a variable that will produce B's and C's in pairs. Okay, so that's one rule. We're going to create the prefix of A's and a suffix of pairs of B's and C's. So all A needs to do is be able to create 0 or more A's. Okay, so this rule will create as many A's as we want. Okay? And we could have written it differently. We could have written it as AA or epsilon. This would have done the same thing. Okay? It just depends on how we want to think about the A's spreading out. Okay? Now the rule B, we've actually seen rules that do this before in the language B to the N, C to the N. So we're going to use the same idea. We want to create a B for every C, and we want to think about them as creating from the middle. Okay, so this is going to do, so if we have BBC, then we could apply the rule again, and we could apply the rule again, etc. Okay, so that's going to create as many pairs. I'm calling them pairs, but really all of the B's are on the left and all of the C's are on the right. But the point is that we're going to generate the same number of them at the same time, so one B for every C. And we're also respecting the order. So the B's are always going to be to the left of all of the C's. Okay, and in order to terminate this string, we need to also be able to turn a B into an epsilon. Okay, so that applied to our little suffix here would take that guy out and we'd have BBBCC. Okay, so I claim that this is our entire grammar that we need for this language. So first, just in the interest of being formal, our set V of variables is S, A, and B. Sigma, our set of terminals, is A, B, and C. And our set of rules, we can see above, and S is our start variable. Okay, so this is our fully defined grammar G. So if we want to convince ourselves that G actually generates the strings in this language, or that any string in the language L1 has a derivation in the grammar G, we want to note that one, order is maintained. Okay, so what do I mean? Any string that has a derivation in this grammar will have all of the A's in the first part, right? That's because of the way we defined our rule S goes to AB. Any A's that we can create will always be to the left of any B's and C's. Okay? B's will always be in the middle part. This has to do with the rule B. The rule B goes to B, big B, C is always going to put B's to the left of C's, and then back to our argument about the rule S goes to AB. A's will always be to the left of B's, so we know B's are always going to be in the middle, and then we know that C's will always be on the end. Okay, so that's the first thing we need to check. The second thing we need to check is that the number of B's is always going to be equal to the number of C's. And we made this argument as we created the rule. So the rule B always makes one B for every C and one C for every B. So we have definitely created the same number of B's as C's. Okay. Also, we could also check the condition that M and N are greater than or equal to 0, right? So this means let's let, I'm going to do it over here, I'm running out of room. Let's let M equal 0, and N can be anything. Okay, so what was M? M was the number of A's. So if I take the rule S goes to AB, and then I take, so let's make this a, derivation. So if I do S yields AB, and then I replace A with the rule A goes to epsilon, I'm just going to have B. And then B is going to allow me to create any number of B's and C's. Okay, so M can be 0 or more. If I do S goes to AB, and then instead of replacing A with epsilon, I replace A with little a, big AB, I can get 1A and then as many A's as I want. And likewise, if N is 0 and M is anything, then when I do, I'm going to say some number of derivations that gives me, some number of steps that gives me 3 A's and then a B, I can always do B goes to epsilon, so that just gives me the string AAA, so here N is 0. Or instead, if I took the rule B goes to little b, big B, C, little b, big B, C, I could replace the B with as many B's and C's as I want. I can take that rule repetitively until I decide to take the epsilon rule, and so I'm going to get where N is greater than 0. Okay, and here I did that as well. N is greater than 0. Okay, so we've proved the third condition as well. So this grammar is definitely a grammar for L1. Okay, so we can conclude that the language of grammar G is equal to L1. Okay, what does this mean? This tells us that L1 is an element of the context-free languages. Why? Because I have a context-free grammar that generates the language L1. Okay, so here's our proof that L1 is context-free. Let's consider L2. Okay, so I could make a grammar for L2 and I could do it very easily, right? I just modify the last grammar, and it's a very small modification to make it for L2. But instead, let's make a PDA for L2. So just so that we have this on the same screen, let's put the definition of L2. It's A to the N, B to the N, C to the M, such that M, N are greater than or equal to 0. Okay, so let's define a PDA that accepts language L2. So let's call the PDA P, and we're just going to remember that a PDA has a set of states. It has an input alphabet, it has a stack alphabet, It has a transition function delta. It has a start state, which we're going to call Q0, and then it has a set of final states. Okay? So let's try to create this PDA. We're definitely going to start in state Q0. And remember, we want to be able to detect when the stack is empty. So we're going to use a bottom of the stack symbol. We're going to use the $, as has been the convention. So when the machine starts up, it's going to read no input. It doesn't need to look at the stack, and it's going to push a $, to the stack. Okay, so now we have a symbol that's telling us where the bottom of the stack is. Okay, so now we would be in Q1. So here, I want to be able to read NA. Okay, so I'm going to read A from the input. I don't need to check my stack. Right now there won't be anything on it. And then what should I push? Well, notice here we need to be able to match A's to B's. So I need some kind of counter for how many A's I've read. So let's just push a $. Okay? So for every A I read in the input, I'm going to transition back to Q1 and I'm going to push a $. Onto my stack. Okay, so this PDA is non-deterministic. So at some point, it's going to guess that it has read all of the A's. And at that point, we're going to transition over to state Q2. And notice I'm not going to do anything to my stack. I'm reading no input. This transition just says I have done reading all of my A's, so now I'm going to go over to Q2 and start reading B's. Okay, we're also separating the state that reads A's from the state that reads B's. This is important so that we don't allow the machine to mix A's and B's. For example, let's say I had a transition like this. Okay, so what would this allow me to do? This would allow me to read an A and push a pound symbol, and then read a B and pop the pound symbol, and then read another A and push the pound symbol, and then read a B and pop the pound. So that definitely works for a language where the number of A's and B's is the same, but here we have the additional requirement that all the A's have to happen before all of the B's. So we can't allow this intermixing of A's and B's, so we don't want to allow that transition. So instead, this is why we're separating. Reading A's is all going to happen in Q1, and reading B's is going to happen in Q2. So instead, that's the kind of transition I want for Q2. If I read a B in the input, and I have a pound sign on the top of my stack, then I'm just going to pop it. Okay? So this allows me to read A's and push pound signs, and then read B's and pop pound signs. Alright, so again, we're non-deterministic. At some point, we're going to decide that we are done reading B's, and we want to start reading C's. So again, we're just going to allow a epsilon transition over to a new state that says we're reading C's. So here, do I care how many C's I've read? I don't. I'm not matching C's to anything. I'm only matching A's and B's. So for C's, we're going to allow to read a C from the input. We don't care what's on the stack. We're not even going to look at it. And we're not going to push anything to the stack either. So this is going to allow me to read an arbitrary number of C's, as many as I want. MC's. Okay? So now when I'm done reading C's, I want to transition over to the final state if my stack is empty. When is my stack empty? If I have pushed 10 pound symbols onto the stack by reading 10 A's, and I have popped 10 pound symbols off of the stack by reading B's, my stack is going to be empty. Or I should say, I'm only going to have the symbol $, which is indicating the bottom of the stack. Okay, if I had pushed 11 A's onto the stack, or I'm sorry, if I had read 11 A's and therefore pushed 11 pound symbols to the stack, and then I'd only read 10 B's, I would still have a pound symbol on the top of the stack. So I wouldn't be able to take this transition over to the final state. So the transition reads no input. It needs to have a $sign on the top of the stack, and then it pushes nothing because we're done. So this is going to be my set of final states. or this is going to be my final state, Q4. Okay. So another thing to notice is that, let's say I had pushed 10 pound symbols corresponding to 10 A's to my stack, and then I had tried to read 11 B's. Well, I'm going to get stuck in state Q2 because I'm not going to be able to take that transition. Right? When I go to read the 11th B, there isn't going to be a pound symbol on the stack. There's going to be a dollar sign. So I'm not going to be able to take that transition, and so I'm going to have to reject. I won't be able to read all of my input. Okay? So I claim that this is a PDA for the language L2, and we can just, let's just double check on two strings. Let's check on the string, we'll make it easy, A, B, B, C, C, C. Okay? And let's make our little stack here. Alright, I'm in Q0, I push a dollar sign to the stack. I go to Q1, I read an A, I push a pound symbol. I'm going to run out of space because this pen doesn't like to write exactly where I'm putting it. Let's try this again. I'm just going to refill my stack. See if I can get it more precise. Nope. Alright. So that's after reading the first A. I'm still in Q1. I read the second A. I attempt to push a pound symbol to the stack, and I kind of get it on there. Okay. So now I can't take any more transitions of the form A, epsilon, pound sign, right? I'm out of A's, so I can't take that. So let's take the epsilon transition over to state Q2. So this allows me to read a B and pop a pound symbol from the stack and go back to Q2. I read a B, I pop the pound symbol from the stack, and I go back to Q2. Okay, now I have no more B's to read. I'm going to epsilon over to Q3, and this is going to allow me to read a C without doing anything to the stack, read another C, stay in Q3, and read the last C, staying in Q3. Okay. So notice if I had taken the transition over to Q4 early, like after the first C, then I wouldn't be able to read the rest of my input. Okay, so this non-deterministic PDA is not going to do that. It's going to read all the C's in Q3. Alright, so now I have a dollar sign on the top of my stack. I can transition over to Q4. I've read all my input, and I can accept. Okay, so that shows that this will accept a string in the language. Let's try a string that's not in the language and see where it gets hung up. I'm going to make this a little bit bigger so I don't run out of space. Okay, so let's try, we'll make it easy, A, B, C. Okay, string's not in the language. Nice big stack. So I start off in Q0, I put the dollar sign on the stack. I'm in Q1, I read an A, I push a pound symbol, I go back to Q1. I read an A, I push a pound symbol, I go back to Q1. I non-deterministically go over to Q2. I read a B. I pop a pound symbol from the stack. Now I'm going to go over to Q3 so I can start reading C's. I read the C and go back to Q3. Now I'm stuck, right? I can't take the transition over to Q4 because I don't have dollar sign on the top of the stack. I have a pound symbol. Okay, so this string gets rejected. Okay. Alright, so that should be enough to convince you that this is a PDA that accepts the language. So now let's finish formally defining it. So that I have some room, I'm going to do some of it up here. So set of states, Q0, Q1, Q2, Q3, Q4. What's epsilon? A, B, and C. Okay, our stack alphabet. We use the symbols dollar sign and pound. Okay, I'll define delta below. Q0 is our start state. Oh, are we missing anything? Let's check. Nope, we're not. So I wanted to check that if m and n are both 0, that we can still get through this machine, and we can, right? If we take all of these epsilon transitions across the top, we're going to end up in Q4, right? So we start up, we put the $sign on the stack, we transition, we pop the $sign from the stack, and so we can accept on the empty string, which is important, right? Because both m and n could be 0. So that's a good thing to check. Okay, so back to our definition. Q0 is our start state, and then F, our set of final states, is just Q4. Okay, and so let's write out all of our transitions for delta, our transition function. Okay, so delta of Q0, reading nothing from the input and nothing from the stack. We go to state Q1 and we push a $sign. Okay, delta on state Q1, where I read A from the input and I read nothing from the stack. I go back to Q1 and I push a pound symbol. Okay, delta of Q1, if I read nothing from the input and nothing from my stack, I'm going to go over to state Q2 and I push nothing to the stack. Okay, delta of Q2, if I read B from my input and pound from my stack, I stay in Q2 and I push nothing. Okay, delta of Q2, reading no input and nothing from my stack, I'm going to go to state Q3 and I push nothing to the stack. Okay, delta of Q3, if I have a C in the input and I read nothing from the stack, then I stay in Q3 and I push nothing to the stack. Okay, delta of Q3 on no input with a $sign on the stack, I go to Q4 and I push nothing to the stack. Okay, so let's check. We have 1, 2, 3, 4, 5, 6, 7 arrows and 7 transitions, so we have defined our transition function. Okay, therefore this PDA, so the language of the PDA-P accepts L2, which means that L2 is in the set of context-free languages. Okay, so we've now concluded that both L1 and L2 are context-free languages. Okay, so let's write that here. L1 and L2 are context-free languages. Then, if the context-free languages are closed under intersection, L1 intersect L2 should be a context-free language. Okay, so what is L1 intersect L2? Okay, well L1 said, let's double check, L1 said that the number of B's is the same as the number of C's, and the order mattered, right? So L1 gave us A to the M, B to the N, C to the N. L2 gave us A to the N, B to the N, C to the M. Okay, the number of A's and B's were equal and the order mattered. Okay, so what strings are in the intersection of these two languages? Well, order is going to have to matter, right? I'm going to have all of my A's at the first part, all of my B's in the middle part, and all of my C's in the last part. And in order to be an L1, the number of B's and C's has to be the same. And in order to be an L2, the number of A's and B's has to be the same. So in order to be in both languages, so in the intersection, we have the number of A's is equal to the number of B's, and the number of B's is equal to the number of C's. Okay, so let's write this way. This is L1 intersect L2. Okay? However, this language is not a context-free language. We will prove this in another video. So for this proof, you have to take my word on it, but you can look at the other video to see the proof. Okay? So if L1 and L2 are context-free languages and context-free languages are closed under intersection, then L1 intersect L2 should be a context-free language, but it isn't. Okay? So therefore, where does our contradiction come from? Context-free languages are not closed under intersection. Okay? Therefore, the statement was false.